This is lesson 18 of the quantum mechanics, a mini lecture series titled Pauli's electron spin. So I talked about the Zeeman effect before and how when you place spectral lines in magnetic field as follows, you will see splitting of those lines. Okay, so one line becomes three lines, let's say. So more lines started to appear in experiments, and this ended up becoming called the anomalous Zeeman effect. Okay, it was dubbed the anomalous Zeeman effect by physicists because they couldn't figure out what was happening. Then came along the Swiss theoretical physicist Wolfgang Pauli, and he wanted to tackle the problem. And Pauli hypothesized that there was a hidden rotation which produces the extra angular momentum responsible for the anomalous Zeeman effect. So to explain the anomalous Zeeman effect, Pauli proposed that electrons have this spinning-like property, even though they're not spinning. It's just like charge and mass. It's a measurable property, how it behaves, to do with how it behaves in a magnetic field. And at the same time, funny story, actually tragic story, two young Dutch physicists had the same idea, and they actually published their paper on this, and because the professor was much more, let's say, lenient, and they won a Nobel Prize. And Pauli missed out on a Nobel Prize. So Pauli proposed there was two possible states an electron could be spinning, clockwise, as such, and anti-clockwise. Clockwise was called spin up. Anti-clockwise, spin down. Okay, think of a spinning top. Here was the condition. Now, mathematically, Pauli worked out you can only have half values of h over 2 pi. Okay, but this is a semi-classical concept. Okay, and in order for this to work, the electron would have to spin, go around twice the nucleus to go back to its starting point, which we know is not correct. So to solve this problem, Pauli proposed that each atomic state contained only one electron. Okay, and when one state was filled, the next state would get filled, and so on and so forth, like as follows. Arrows indicating the direction of spin. And so now we've got the three quantum numbers n, k, m. N is if you recall, n is the size of the orbit, k is the shape of the orbit, and m is the direction in which the orbit is pointing. And you've also got a fourth quantum number, give it symbol S, for spin. And spin can take the values plus or minus a half. So plus a half or minus a half. Plus a half is spin up, spinning clockwise. Minus a half, the electron spinning anti-clockwise. And in quantum mechanics, I'll get to this later, there's this weird thing where electrons, before you measure them, they can actually be either spinning both up or down, up and down, I should say, at the same time. Once you measure them, they actually become, you actually see them as either clockwise or anti-clockwise in terms of their spin, which is really weird. But it's significant in the sense that Pauli was able to describe why atoms are stable, and he did this by introducing the spin quantum number. Okay, and this applied to all elements. So it's one extra piece of the puzzle to explain what was happening due to the anomalous Zeeman effect. So suppose you've got n equals to 1. Okay, the possible orbit shapes, you can have k equals to 1. And the possible direction, the only possible direction is m equals 0. Okay, very minimal energy state. This is called the minimal energy state because the orbit is just, the orbit corresponds to the very first energy state, n equals 1. This is called the ground state. Okay, the state of the electron, the energy level that's closest to the nucleus. Okay, two possible spin states, you can have plus or minus a half. And so therefore you get a total of 2 energy states for an electron. Okay, in n equals 1, the n equals 1 shell.